have. It's possible I'm doing this exercise so we'll discover dark matter. Maybe not. I don't know. Maybe not. Also, how are people going to this? This is a very hard word to write. Planets are pressureless fluid, and prayed on this spot many nights a day.
Thank you.
No problem. Looking at his previous analysis that he did, nothing
Second? No. My watch says 9 as well. Want to say something? Yeah.
So before we start, at the end of the first lecture, I think we're going to be taking a group photo. So we're going to hurry you all over to Barron Field, which is where the photographer likes to take pictures. Don't stop for coffee. Okay. We'll be hurting at the end of the talk here. So off to the real world again.
All right. Great. Good morning, everybody. Just a quick reminder, I really appreciate it if people can wear masks during my lectures. And if you need one, they're over there. All right. So yesterday we spent a while talking about accelerators with some hints of the LHC. I just wanted to check any questions outstanding from yesterday before we start. And can everyone hear me at the back? I'm not sure the microphones. Everyone hears me. Okay, super. Any questions? No questions. All right, so today we're going to start by talking a bit about the Large Hadron Collider. Also known as the LHC. Okay, so the Large Hadron Collider, I don't think we were very creative in the naming. So I think the name tells you precisely what it is. It has a circumference of 26.7 kilometers. And this translates into a curvature of 2.8 kilometers. And it's located 100 meters underground. The underground thing is kind of interesting. Don't know if anyone has an idea why it might be underground.
Backgrounds?
Backgrounds? Could be, but not so much. Anyone else? Say louder.
Human contact, people were going to vandalize stuff.
Not kind of, but not for vandalism. One is just to protect from the fact, we get radiation that comes off the beam. And so putting it underground, you get natural one. Second reason is money, actually. Turns out, not every country in the world has the same convention about how deep they own the land, right? One doesn't think about these things. Switzerland, all the way to the core, You've got your slice all the way down. France actually stops just below sort of 100 meters. And so the fact by putting it underground, and in fact, if you look carefully, most of the access points are actually in France. It's carefully designed. Meant they didn't actually have to buy the land for it. So that's one of the reasons. I'm not sure what it is. Okay, something I should look up to know. So the beam energy, the design value is 7 TeV. We haven't quite got there yet. In fact, for run 2, which just, finished a few years ago, we got up to 6.5 TeV only. And there's a kind of simple formula here. So if you do 1 over rho, this is an approximate formula, something like 0.3 B over P. All right, so once you dug your tunnel, your curvature's fixed. We don't get to change it, right? And so what it basically tells you is that the strength of your magnetic field effectively tells you how high you can get in energy. And so that's actually what limits the LHC. It's the magnetic field that we can get in the dipole magnets, which I'm going to talk about in a bit, which allow the particles to circulate. And so this 7 TeV, this corresponds to 8.33 Tesla magnets. And they're hoping to get to 13.6, I believe, for the next run. That's kind of starting up right now to do it. And then we'll see what happens at high Lumi LHC if we can get all the way to 7, but it's not clear that we can. So even these small differences are actually really hard. So I mentioned the dipoles. These are pretty big magnets. Sorry, question.
Is there anything anyone's particularly excited about looking for in that like little bit of extra energy range?
No, to be frank. So if you actually calculate cross sections for various physics processes, the additional energy reach you get is small because we've got a lot of luminosity, right? Because Lumi and energy can kind of compensate for each other. This is more from an accelerator perspective. They want to get to their design energy, right? It's also a physics experiment for them, not just for us to do it. For us, it's annoying because we have to remake all our Monte Carlo. Slightly different energy. So we have lots of dipoles, 1,276. They're almost about the size of the width of this room, more or less, to do it. 15 meters long. And if you get to visit CERN, which I guess some of you have done, you can actually, there's a dipole, some spare ones kind of sitting around. And so you can take your photo sitting on a dipole. They are superconducting. They're made of niobium titanium as a superconductor, and they operate at 1.9 Kelvin. So in fact, this is super cold, right? It's actually colder than outer space that we have to have. And so you can actually think of the LHC as one of the largest cryogenic laboratories in the world. The current they have is almost 12,000 amps. So you absolutely don't want to go touch that. And they have 2 bores. What I mean by that is 2 holes, basically right down the center. One for the protons going one direction, one for the going the opposite direction to do it. I've lost my second board. Or have I? Oh no, here it is. Okay. Then we have other magnets. These dipoles, right, they're just used for steering the beam to really make it go in a circle. Thank you. Wait, what was that? Light? Super. And for example, we have quadrupoles. These are used for restoring or anti-restoring. And if you think back to that luminosity formula that we talked about yesterday, it's about squishing the beam, right? So we want to make the size as small as possible. And you can do it independently. You can do it in the X and in the Y direction to do it. Then there are various higher order magnets, which are used up to decapoles. Okay. Then some things I'm going to leave out because we're a bit short on time. There are various properties. Yeah.
Oh, thanks. What do you mean by restoring and anti-restoring?
I mean this direction or this direction. So what I mean is you can orientate your quadrupole with its 4 poles, by definition, such that when you have your beam of charged particles, it squishes them like that. Or you can orient it such that it squishes them like that. And in reality, you do both, not at the same time. But things that matter, which I'm going to sort of leave out, but we can chat about them later if you're interested. there's the beam emittance. This is just trying to confine particles to a small distance and have a small range in momentum. And then there is the amplitude, which is known as the beta function. And in particular, there's the amplitude at the interaction point, so where they collide. And that's what we want to squeeze as much as we can to get to high luminosity. And so that's the beta star function. That's something that will be changed to LHC. All right, I want to show. Actually, no. Yeah, I want to show the picture of the LHC now. So let's see. Let's see how well this works. Just so you have some idea of it. Okay. Lovely. Okay. We get it 3 times, but we'll make those go away. All right. So there we go. That's a picture of the Large Hadron Collider. So you can see this almost 27-kilometer ring. You can see Mont Blanc over there, Lake Geneva. In fact, that's the airport just at the side there. You can see the main CERN site, Meran. There's a second one at Prevesa. And you can see 4 of the big experiments, which are labeled here. And you can see a little bit what I was saying about the border. This dotted white line, that's the border between France and between Switzerland. Now let's see if this works. There's one thing I wanted not to make the sound because the sound is very annoying. Oops, we don't want that. Oh, well, let's try it and see if it gives sound. No, perfect. So what you're seeing here is you're seeing different bunches go through the accelerator chain at the LHC. And so these are actually old accelerators from CERN that were previously used for different physics experiments. And what is done is that at each step, the bunch of the protons get accelerated up to higher and higher energy. Now we kind of jump inside the LHC itself. Here you see in blue, those are the dipoles, not cool graffiti, of course. And we're sort of going along in the direction of the beam. In a second, we're going to kind of jump inside. And now you can see an image of what might be going on inside the proton. Artistic license. Up ahead, you can actually see an experimental cavern. And it's timed here such that the 2 bunches are going to collide right at the center of Atlas. Then they get destroyed, produce a whole bunch of particles. You can see all the detectors lighting up, things like that. And you can notice there are kind of some long tracks going through the detector, which we're going to color in here to see it. Anyone want to guess what event that might be? Say, someone? Muons. How many muons? Right, so anything we know that could decay to 4 muons, that's kind of interesting. 2 Z's, which come from? A Higgs boson. So it's a Higgs to ZZ to 4 muons, just as an example event. Now, you might be wondering, why do we have all those steps in the accelerator, right? Why don't we just stick the protons in the LHC? If you think back to the formula, which is hiding now, right, there's a coupling between the curvature, the magnetic field, and the energy. In fact, the dipoles in the LHC, they couldn't go to low enough energy to actually start out. And so if we use a smaller ring, magnets with lower energy, we can actually step up all the way through. And also it was free because we had those ones already. Okay. Now this goes a little bit to questions people asking yesterday, which is about the LHC life cycle. So I'm going to draw you a little bit of a sketch to tell you how it works. So this is time, and we're going to start by injecting the beam, and we do it in steps. So you go step by step to inject it. Then we get to the top there, go along for a while, like that. Okay, and so this is injection here. And then an injection ends over there. Then what I'm going to draw is a second curve, which is actually going to show you the energy. And what happens here is we start to ramp the energy. So when the particles come in, they're actually only at 450 GeV. We do the injection like that. Then we ramp. We get all the way up to 6.5 TeV. Then what we do is we do the squeeze. So that's what happens here, i.e. we make the beams as small as possible so we can maximize the luminosity. And here we have what's called stable beam. And this continues, and then it's going to ramp down. So I have two things here. You can see the beam current and you can see the energy. And what happens over here is you notice we've kind of lost quite a few of the current in the beam. This is because we're doing collisions, it's natural. And so this is known as the dump. That's where we take the beam, we send it off to the dump, and we're done. And then we repeat this process over and over. Amusingly enough, if you get to sit in the control room for one of the experiments, the sound that you get for the dump is a toilet flush. And so when you hear the toilet flushing, then you're like, okay, we've got to quickly get the detectors into a safe state because they're going to dump the beam. The time for this can vary a bit. If it's a good fill, it can be something like 8 to 10 hours. I think our longest was like 24 or something. At the beginning, it used to be 1 to 2 hours. And from our perspective, there's a lot to do because only in this phase can we have our detectors fully up and taking data. So we have to protect them, we have to turn off voltages and things, and so these other parts of the cycle, these really take quite a bit of time. Okay. So now I'm going to talk a bit about the experiments. Yeah, question.
Hi, so I'm just wondering, for the high luminosity LHC, what particles are they upgrading?
The luminosity.
Well, does that mean they're focusing the beam more, or having more bunches, or what were the bunches?
So I believe the predominant one is this beta star function that I briefly mentioned. We're going to be able to focus the beam quite a bit smaller to do it. And so what that's going to do is that's going to increase the luminosity. It's also going to increase the pileup. Yeah. For the LHC or for the detectors or for everything? You're not bored usually to do it. No, so LHC has their own control room. Typically, there'd be like 5 or 6 people there in stable times to do it. And then each of the experiments, we would also have 5 to 10 people around. A lot of the stuff is automatic. However, things go wrong, and we're dealing with multi-million-dollar detectors. So like not having someone there, right, to intervene when a computer program has a bug can have quite large consequences. So we're a bit conservative in terms of the amount of people that we have to do it. And things go wrong. It's a very big, very complex system. So even as much as you try to automate it, often there are things you have to deal with. I mean, I'll give you an example. So I took the last shift of run 1 or run 2, one of them. And so I wasn't on shift. I was the person like on call to deal with problems. And so the plan was, 7 a.m. they're going to switch off the LHC and we're done, to do it. So we had everything set up. Someone was going to come turn off our magnets because that's a big intervention. There's someone special to do it. So I wake up and I look at everything. I'm like, we're still taking data. But what's going on? Our magnetic field's going down here. So I kind of phoned the control room. Eventually what I figured out is what happened is the person who was responsible for turning off the magnet, they just walked in, turned off the magnet without talking to anybody at all. So Atlas was happily taking garbage data, right, while the magnet ramped down. So yeah, we lost a little bit of data from that to do it. But this is the sort of thing. There's a lot of pieces and humans and various things one has to think about. Yeah.
Yeah, so sorry if you already answered this, but okay, so when you turn on the machine, so what is the runs like? Like how long does it last? How long do you take data for?
So that picture there, right, there's also about 2 hours of prep, which I'm not doing. Right, so they can't just turn on and inject immediately. They have to do various things. Typical stable, like physics, stable beam run could be something like 8 to 10 hours. But it varies a bit. But you can see that the luminosity is decaying. So there's a bit of an optimization question, right? Like you lose time in the overhead each time you do a run. But as the luminosity decays, at some point it makes sense to do it.
So the batteries are running around for over 8 hours?
Yeah.
Oh, wow. And then you just shut it off and you upgrade it?
You dump. Then we pre-cycle, actually, is what it's called. And then we inject again and we repeat. But it's not constant. It's not like, it lasts for a certain amount. The beams are not always identical. Like, it can be good beam, it can be a dirty beam. You can see that. Yeah.
There's a period of time where you have the highest energy and not decreasing luminosity. So is that period?
That's the squeeze. So that's actually before collisions. So what they do, right, they put the beam in, they accelerate it up to the high energy, then they squeeze it, then they collide. So it's not actually colliding at that point in time.
So for experimentalists working on analyses, how do they control all these different factors for like when the data run has a bad beam?
So luckily what we do is we try to protect people from that as much as possible. So we have a data quality group. And so every single run, there are people who examine the data from every single detector, and they set flags, like green or red or orange, to do it. And so orange, sometimes we can recover, depends what the problem is. And then in the end, when you do your analysis, the simplest thing is you just require all the flags to be green. And you lose, I think, something like maybe 2 to 5% of the data to do it. You can also go in, and so we go in and we try to fix it as much as we can, and you can recover a little bit more. But yeah, it has to be done every single run. Some automatic, but there's an official sign-off that we do for each one. Because yeah, you're right, missing calorimeter tower can discover a new particle. It's as easy as that, but not really very new. Yeah?
So then the detector is running for some period of months, and then, how often are the intervals when you upgrade the detector?
That's much rarer. So this normally happens for 10 to 11 months of the year. So there's a shutdown at Christmas because that's when power is the most expensive to do it. However, and so big upgrades, so small upgrades can happen then, but big upgrades can only happen in a long shutdown, and those happen between the runs to do it. Very small stuff can happen between fills, right, when the LHC is doing things. And every so often, they might have a few hours where they have to do things. And so, but time is really, really precious. So when we have those intervals, you phone up the people, even if it's 2 o'clock in the morning, saying, hey, you've got 2 hours, want to go to do it. So it's really quite tricky, managing these things. You can't expect that, you can go in and fix your detector every day. It doesn't work like that at all. All right, so I'm going to stop questions here because I want to tell you a bit about experiments. We can talk later. First question, who can tell me how many experiments do we have at the LHC? 5. Anyone else want to guess? I heard 6. I heard 7. All right, let's see the list. It's more than you think. Notice I said big experiments, right? Okay, so let's start with the easy ones. We have Atlas, and we have CMS. These are the 2 general purpose detectors. Then we have, I'll come back and talk about them in a second. Then we have Alice, does heavy ion collisions. We have LHCb, does B physics, also a few other things these days. Then we have some more. We have Totem, and we have LHCF, and we have Moidal map. And finally, we have our newest experiment. I think someone works on this one, which is phasor. Right, someone works on phasor. Yeah, you do. So 1, 2, 3, 4, 5, 6, 7, 8 experiments at the LHC. And I'm going to tell you what they are in a second. Don't worry. I'm not just giving you a whole bunch of acronyms. Moidal map. That's a P, sorry. Went very wrong. Okay, so let's talk about them for a sec. So Atlas and CMS, these are the ones I work on Atlas. These are known as general purpose. What that kind of means, right, is they're designed to measure as much as possible. So kind of measure all different particles that you can think about so that they're able to do a wide range of physics. Things that we do are precision, standard model measurements. For example, things like W mass, top mass, etc. We also study the Higgs boson. And I need a better piece of chalk. And we do searches for new physics. If you think about it, these can be a bit competing, right? So if you want to do searches for new physics, you want to be able to go to as high energy as possible, right? Or you want to be able to search for crazy signatures. For precision standard model, here we want to have things done as precisely as possible. And so there are sometimes competing requirements that one has to think about in these. At least, this one is when we actually fill the LHC, which I haven't talked about at all, with lead ions or other ions instead of protons. We can do that. And the goal here is to make as high an energy density as possible in a small area. And they want to study something which is known as the quark-gluon plasma. This word isn't well chosen, but that's okay. That's because the name was chosen before they knew exactly what it was. And the idea is trying to study what happens to quarks and gluons once you go like what happened super early in the universe, where they were mostly deconfined. LHCb is primarily after B physics. Wants to understand things about CP violation. And these days, I think one might say, is they're studying anomalies, primarily in B physics. Yeah?
Does at least just spend most of the year off then and not doing anything?
Not exactly. So for a lot of their measurements, they actually want to study the lead-lead system relative to proton-proton. So they take proton-proton data for that. However, by the nature of the detector that they have, they can't handle high luminosity, and so they take data at much lower luminosity. Only Atlas and CMS take it at the highest luminosity to do it. Yeah, heavy ions is usually a few weeks to a month a year, and that's highly contested, right? You know, deciding what physics schedule they could be. There are all sorts of meetings and people arguing for whatever topics they want.
Not taking data during the lead
So both Atlas and CMS do have a heavy ion physics program. They do take data during it mostly. LHCb does not to do it. It's really left up to the experiments to decide what they want to do.
So LHCb is exclusively looking at proton-proton then?
Mostly. I don't believe they've looked. Sometimes they do some interesting luminosity measurements, which might happen during heavy ions, but they don't do any heavy ion physics. The detector is not designed for it, basically. All right, now then let's talk about the smaller experiments. So Totem, this one is actually near CMS, and LHCF is near Atlas. And what they're after is doing forward physics. What we mean by that is that they're located, a couple hundred meters down the beam pipe, and they're looking for particles that are produced in very, very forward directions. And so, for example, this is how we get a total cross-section measurement at the LHC. So we have these smaller dedicated experiments to do them. Then Moedo map, this one's actually either side of LHCb, and they are looking for magnetic monopoles. Of course, since you haven't many of you haven't heard of them, that means they haven't found any yet, right? Because had they found one, we'd all be hearing about that a lot. And then Phaser is, again, near Atlas. Again, I think about 500 meters forward. And they're looking for new light particles. You know, some of the crazier ones that phenomenologists can make. And actually, more recently, they're actually studying neutrinos that get produced at the LHC to do it. Then there are actually a whole bunch of ideas. Some of them you might have heard of. There is Methuselah. This is one which would be above CMS, looking for really exotic, long-lived particles. There's one called Millikan. Actually, I don't know how to pronounce it. Looking for milli-charged particles. And then another one is called Codex B, which would again be near LHCb, also looking for long-lived particles. And so these are at various different stages of demonstrators or proposals or things like that to do it. But what you can see here is that having an accelerator like the LHC can really provide a rich program of possible experiments that you can do to try and study, you know, all the cool ideas that you guys actually come up with. Yeah.
I don't know how much detail you'll go into.
No, not much.
Codex B, I've never heard of. What exactly are they doing?
They're also doing long-lived particles. They're similar to Methuselah in terms of the physics goals, but they're quite a bit smaller. And
Would it be on the surface?
no, they would be underground in an old cavern near LHCb to do it. I think Millikan is in the process of getting built, so a good chance of happening. Methuselah and Codex B are getting close. But I heard some stuff about Codex B recently, so it might be that they managed to get built sometime. Yeah. We wouldn't see them very easily in the existing detectors. And the thing is, like these experiments, they are really much smaller and have much smaller budget. And so it typically costs nothing, basically, for the overall program, right? To say, okay, you've got funding, you want to build your detector and stick it in to do it. And so it's a little bit like that, right? They're non-destructive to do it. And so if people give a good proposal that makes sense and is accepted, then typically they're allowed to do it. Okay. So now I want to switch a bit and talk about how we detect particles. Oops, great. And here it's a little bit more interesting than accelerators because we actually get to use 3 relevant interactions. I.e., we can use electromagnetism, we can use the weak, and we can use the strong force. And the way it works is you have to think about the different types of particles that get produced and how we can actually detect them. First one, and that's what we're going to focus on mostly today, are charged particles. These can be either leptons or hadrons. We don't care, we just care about their charge. And here we're primarily detecting them via ionization. Then you can think about photons. Photons, here you can have pair production, right? Where you can have a photon that produces an electron-positron pair. Actually, I'm going to see if there's any bigger chalk. Yes. And again, once you've done that, then there's ionization. Then we have neutral leptons. We're just talking here about neutrinos. These are pretty tricky. So in fact, in most of the LHC experiments, we detect neutrinos through missing energy, through the lack of them. But more generally, you can detect them through weak interactions. These would be other types of detectors. How about quarks and gluons? The products of the strong force. Of course, as you know, right, there's no such thing as a free quark or gluon to do it. So we cannot, you can't build a quark detector or something. What actually really happens here is they are combined into hadrons. And then speaking of hadrons, here we're looking for, and this is for both charged and neutral, here we're looking for nuclear interaction. You have some detector with the nucleus, which will actually interact with these particles that are passing through to do it. Damn it. So that's loosely speaking about the various ways that you can think about detecting them. Of course, it's pretty easy to write that down in kind of one line, right? You've also got to think, how do we actually go about building a detector that could actually do it? The other thing to think about, this was just how do we measure the different particles. Then you can also think about the different kinematic properties. There is the energy, which can also be the EDX. Here what I mean is the energy lost over some small distance x, also known as the stopping power. And what we do here is we really stop the particle in the detector. Here we could either use something like electromagnetism or the strong interaction, and then we can measure the ionization energy. One thing to kind of notice here is when I talk about stopping a particle, by definition I've kind of destroyed it, right? If I've stopped it, it's gone. And so there are kind of two types of measurements. They're the destructive and the non-destructive, right? So in some cases, we just want the particle to stop, want to learn about its properties, and we don't care about it. In other cases, we actually want to learn about the particle, but we still want it to be able to continue. So we try to spy on the particle without actually stopping it. And that's what we do when we're interested in measuring the momentum. Primarily what we do here is we look for the trajectory of a charged particle in a magnetic field. Right? This goes to simple things. If you put a magnetic field, you have a charged particle, it's going to bend. And indeed, the amount that it's going to bend is actually going to be proportional to the momentum of the particle. And so if you can measure that, you know how fast it's going. Finally, we would like to know P over the absolute value of P, which is the trajectory. Whoops. i.e. we want to know the positions of the energy deposit. And the reason for this, right, is quite often we would like to know, where was a particle produced? Which direction is it going? Because if you think that you want to actually go back to the original particle that it was produced from, you need to have that information. Any questions? Yeah. Sure.
So, if we're looking at particles ionizing the detector material, don't we have to replace them every once in a while? Or?
Haha. Yep. So yes, our detectors get destroyed to do it. They actually get primarily destroyed by the beam background, right? So from extra particles, not necessarily the ones we're measuring. But indeed, each time when you're having these particles ionizing, if there are enough of them, it can destroy them. And that can particularly become an issue for silicon detectors. And so that's why for both Atlas and CMS, for example, we're going to completely replace the silicon detectors before the high-lumi LHC because they have too much radiation damage.
So right now they're running what's in there right now has been going for the past 3 months?
CMS actually upgraded their pixel before and during run 2. In Atlas, we added an extra layer at the innermost for ours at the beginning of run 2. But otherwise, the rest has been running. And you can see it. You can see, like, if you monitor various properties from the radiation damage, that they are getting damaged and working slightly less well over time.
I see. And I have another question on this Leptons hadrons through nuclear reactions.
Yeah.
So what exactly do we mean by this? Am I seeing some kind of like scattering, or am I breaking up the material? Or?
No, so we'll come back to that tomorrow more. We're going to talk about hadronic calorimeters, right, which are designed to capture all the energy from the hadrons. Again, here it's like the ones I was talking about, the destructive measurements. This is what calorimeters are going to be used for. But I'll come back to that more tomorrow. Yeah. So it does a bunch of things. So it can make inefficiencies. For example, like when a particle passes through, right, we want to say, yes, a particle passed through. Some of those get lost to do it. It also makes extra noise. And so that would mean you get a spurious signal where there isn't a particle to do it. I mean, the reason that we can, right, is that we have efficiency in our measurements. So in terms of physics performance, we can essentially compensate for the moment. But that's not always the case. And if we didn't replace them for high-lumi LHC, it would start to have an impact on the physics measurements. I mean, this is known, right? So they were kind of designed for a certain amount of luminosity, taking into account that this would happen. Okay. So the last piece, which I'm going to be super brief on, you can take an entire course on this, is interaction of charged particles in matter. And that's because for the rest of today, I'm going to be talking about tracking detectors and also, how we would actually find tracks in them. There's actually a great review on this in PDG, which I encourage you if you're interested. In fact, I refer to this pretty regularly. So I tried to make a small URL. Hopefully I got it correct. Otherwise, you can Google for it. Which has a nice review, which will give you, a bunch of pages about all the different interactions. So kind of what we're after here is these can deposit energy, which we've been talking about. And this is primarily done if you think about your detector, and there are going to be 2 types we'll talk about. There are gas detectors and there's silicon detectors that we have. But essentially what we're after is we're after ionization of the atoms that are the detector material to do it. And if you actually have a look at this, you can look at, for example, given a particle, what is the average ionization loss? This is what we call that dx I spoke about. This actually ends up following a Landau distribution to do it. So it looks something like that. Okay, that's a terrible Landau. That looks exactly like a Gaussian. Landau is kind of a bit more like that, right, in terms of the distribution. And that's the distribution of the deposited energy. Most of the time what we're after is we want to know the most probable value, right? Not quite the mean, most probable value. But quite often there can be significant fluctuations. And you can see that, right? There are long tails that we can have to do it. Now, if you want to understand this energy loss, we have a good distribution, which is beta block. Again, have a look there. You can see all the different types and regions that we have to have it. But that's not all that happens. It's not just, a particle goes through, ionizes your atoms, you're done, that's it. In fact, the matter also affects charged particles. What I mean by that is that we can have an effect which is known as multiple scattering. And this is kind of an undesired side effect from the fact that you really need to make your detector out of real material, okay? So what happens, right, is your particle goes through, gets to, some layer of your detector or some straw or something, and its trajectory gets changed by the interaction. This is what's known as multiple scattering, because typically for a trajectory passing through, it will actually look, I'm exaggerating a bit, but something like that to do it. And each time there is one of these scatterings at some piece of material, your particle is going to lose some energy, right, through that interaction. The other one is Bremstrung. Oops, I always spell Bremstrung wrong. I think it has two S's. What this one is about is the fact that you can have radiation of photons from charged particles. And this one only happens when you're in some sort of matter to do it. This effect can happen for any charged particle, but it is most important for electrons. And what actually happens here is that if you think about, let's say we're again looking for a Higgs boson. This time we're looking for a Higgs 2 electrons, 4 electrons instead of 4 muons. If you neglect this effect, this Bremstrung of the energy loss, you end up with a significant bias for the mass of the Higgs boson. So what we actually do when we're reconstructing it is we look around our identified electrons and we try to identify these Bremstrung radiation that we have, collect up all that energy, and actually correct it back to do it. And so it's known as Bremstrung recovery. Any questions about that?
There are detectors special for the Bremstrung to detect
Well, sort of. So what we'll come to tomorrow is that for electrons, we actually combine the trajectory, which we talk about today, the tracking, with the calorimeter measurement. And in the calorimeter, right, you're just collecting up the energy. So as long as your Bremstrung doesn't really have too big an angle, you should be able to collect it together in the calorimeter to do it. But sometimes it does, and that's why we do this recovery process to do it. So you can recover it, just take some work to actually do it. Okay. So now we're going to talk about putting this kind of together into tracking detectors. Here what we're after is to simply measure properties of charged particles. Which charged particles, you might be wondering? Truthfully, we don't care, right? Anything that has charge, a tracking detector would be able to measure it. Primarily, though, we're measuring pions, measuring electrons, and we're measuring muons. That's most of what we actually see. But if you come up with some interesting exotic particle that's charged, we can think about using our tracking detectors to be able to detect them. And we're going to measure the trajectory. We're going to measure the momentum. We already talked about how we do that. And sometimes, depends, not all of them can do it, we're going to try and measure the species, i.e. which type of particle we would actually have to do it. For example, ATLAS and CMS are not very good at identifying the species. There's actually other particles. You can have kaons, etc., to have it. But both LEs and LHCb, they actually have good particle identification capability. So we can partially do with ATLAS and CMS, but not particularly well. Yeah?
What do they have that ATLAS and CMS don't?
So, there is a way that you can actually look at this energy loss versus momentum, and so it depends on your resolution to be able to separate it. Also depends on the momentum range in which you can measure. So this particular method, the one I'm thinking about, works well at low momentum. But ATLAS and CMS are more optimized for higher PT physics, so they're not so good in that range. There are also specialized PID detectors, which I think I will not have time to tell you guys about. Things like ray imaging Cherenkov detectors. Because if you can measure both the momentum and the velocity, then you can easily get the mass of a particle and know what it is. So again, like building your detector, there are this huge array of options, right? And you've got to think, what is the physics we're doing? What's the best way to put it together? And so it's quite an interesting problem. I think there was a question. No?
Oh, I have the same question.
Oh, same question. All right, different question.
You mentioned this Cherenkov detector to look at the velocity, but isn't it pretty easy to look at the velocity? I can look at when I hit the tracker here, when I hit the tracker here, and get a distance over time.
It gives you no, we don't have time.
On the trackers, there's no time?
Not at the moment. That's actually one of the R&D things that people are thinking about, is how to add timing to do it. We don't have a timing resolution, right? So we have timing, we can know which bunch crossing it came from, like which collision, but we cannot tell for the hits.
It's just not sufficient resolution?
Nope. These go fast. Yeah.
So you mentioned you can measure the magnitude of P by B field and direction. So do you have like the tracker with B field and the tracker without?
No. We can turn off our field, but that takes like a couple hours to do it.
So basically the second one is just like the retracing the curve.
It's just doing the trajectory that we have to do it. And then sometimes, like for example, for something like an electron, we also get the energy, right? We don't get that for a pi plus, because it wouldn't interact in the same way in the electromagnetic calorimeter. But actually, I'm going to say a bit more about the B field, so it's good you asked that. So most of the time, they are in magnetic fields for exactly that reason, that we're after the momentum. And the way that this works is that if you look at the P over Q, so momentum over charge, this is going to be equal to B times rho to do it. And what that means, if you think about it, is that the higher the magnetic field you have, and these are different ones to the LHC, right? We're talking about the magnetic field we have in the detector, you're going to get more curvature, right? So CMS, for example, they have twice the magnetic field of Atlas, so it means that their tracks are way more curvy than ours. Ours would be a bit straighter for the same, I mean, that's way exaggerated for the same track. And it also shows you a limit to this technique. If you have like a really, really high PTE track, I don't know, like 500 GV or 1 TV, it's going to look pretty straight in the detector. And that means you're going to have very poor momentum resolution measurement. So trackers, you have to sort of tune them a little bit. And most of our trackers, they're sort of good in the range of something like 0 to 40. Actually, 0 is a lie. Maybe 0.5 to 40 GV. This is the momentum where they're the best. They can keep measuring for quite a while, but it starts to degrade to do that. Now, we can turn the magnets off. Sometimes we do that. It takes like an hour or two, so it's not something you can do easily. And it has stress on the magnet, so you choose carefully to do that. But they did that, for example, to do some sort of alignment studies, which is where we're checking, is the detector exactly where it should be to do it. You could also reverse it. If you were looking at some really crazy new physics signal, you could reverse it and see if everything flips in the way you'd expect.
So when the detectors were being designed and people had a pretty good guess about where the Higgs mass was going to be, why wouldn't they optimize that to be in the range of Higgs mass?
We didn't know what the Higgs mass was going to be. So before, when LHC took like 20-something years to design, we knew that the Higgs was going to be somewhere, I guess, between 50 GV and 1 TV. So you actually needed to design over the full range to do it. So the Higgs boson played an important role, but if we'd known the mass, it would have been a lot easier to do it.
I guess my question still stands, though, this only goes up to 40 GeV.
It's not up to 40, that's where they're best. So, I mean, we can still measure 100 is fine. It's when it's 1 TV that the resolution gets bad to do it. Doesn't mean you can't measure. It just means you measure less accurately to do it. And so, for example, let's say we wanted to study a charged particle of 200 GeV, right? Let's say we found some new physics signal or something. Then we'd want to build a different detector to do it. We need to make it larger, right? We could make it larger, the lever arm that we would measure it on, or we try to have a higher field, or we think about different ways of doing it. That's more the point. Actually, it turns out they work quite well for the Higgs. We're lucky. Significant. So for example, if you look at like upsilon resonances, so this is like a low PT dimuon resonance that they measure, there's 3 of them very close together in mass. CMS can resolve them. Atlas we can't to do it. But this is true in general, like Atlas and CMS were optimized quite independently. We've given more or less the same amount of money, right, and optimized, and not everything is the same to do it. So there's certain areas where CMS might have a strength and certain areas where Atlas may have a strength, and in low momentum resolution, yep, CMS is better to do it. In fact, that brings me actually very neatly to the next topic, which Atlas happens to be better at. Actually, sorry. Do you mind wiping the board? Because I'm going to reuse it and the eraser's pretty crappy. Sorry to disturb. All right, while he's doing that, I'll do one on the very crappy erased one. Just do the next 2 would be fantastic. Thank you. Actually, I can use that bottom one, yep. Okay. So, there's a second thing that we can do, right, is let's say we've actually got our tracks, right? We can actually combine our tracks together to try and find the vertex from some interaction or decay. What I mean by that is think about our protons. They're colliding, okay, at some point, producing a whole bunch of tracks. I'm cheating, I'm drawing them straight. Of course, they really should be curved. But let's say we have one track here that actually decays to a whole bunch of other particles here. This would be known as our primary vertex. And this one would be known as our secondary vertex. And what I mean by that is you think about all these particles, right, coming together in a certain point in space to do it. And this was going back to your question about differences. Atlas is actually better in terms of the secondary vertex resolution than CMS. And this is due actually to the design of the tracking detectors. Now, there are actually two main types today of tracking detectors. And these are gaseous wire chambers and silicon detectors. And they are various different incarnations of each of these, right? So there's sort of a basic principle about how the detector works. And then when you actually think about building your real detector, there are various ways of doing it. But sort of loosely speaking, for a gaseous wire chamber, what we tend to do is we have, let me just draw the picture. This is a tube, okay? And my tube is going to be my cathode. And then down the middle of it, I have some sort of wire, which is going to be my anode here. Okay, and it's filled with gas. Type of gas, this depends on the detector application that you have. There are various different ones. Often they can be various noble gases. Then what we have is we have a particle which passes through, charged particle has to be. And what's going to happen is it's going to, again, ionize the gas as it passes through to do it. And then what's going to happen is that because we have the anode and the cathode, we can actually collect up all the electrons that get produced, and we can actually measure them to see that a particle went through. So that's what it is, typically. There is a tube-like structure, has this wire at the center, the wall is the cathode, and it's filled with gas. And we're really collecting up these electrons through ionization to do it. And then what would happen here is we can look at the energy as a function of the radius. You will actually end up getting this sort of decaying distribution. As it's further away, you end up getting less. And then what you're after is you'll set some threshold, which you'd call E threshold, and you say, if I have energy above this threshold, I'd say a charged particle actually went through. A detail I'm not going to talk about. This is a little bit simplified. Generally, the primary electrons produced in this way are actually not enough to get sufficient signal. So there are usually various different amplification techniques that are applied So you collect up more electrons than is shown in the simple sketch. Now that's great, but that's going to give me one little dot. Yeah, question? It's for one piece within a detector. And I'm going to show you right now, actually, how you'd build a real detector, because that's not very useful. It's just going to say a particle went by, right? And I've been talking about trajectories. That's not going to tell us that. Yeah?
So can you help me understand how this chamber is oriented, like parallel to that? Or?
Yeah, because usually they're parallel to the beam. I mean, you can have end caps as well, which would be a different thing to do it. But this is just thinking, like my interaction I had here, here's a particle going transversely through. That's typically how it's done.
I guess I'm wondering, so I have this tube, I guess, and do I have some resolution that tells me that I hit it here or hit it down here?
So the thing is, right, in many of them, you can actually decide, you can measure the time it takes for it to get there, right? And that can tell you, right, whether you were here or you were there. The simplest one doesn't do that. That just says my wire got hit, but the more sophisticated ones can actually do that. Yeah?
So isn't there a fairly small probability the electrons will hit the wire if they're coming off?
No, because it's a field. So they get pulled to the wire.
Okay.
Yeah. No, otherwise it would not work. Then if they would go the other way.
Okay, and the cathode would detect them?
In many cases, yes. That's typically how it would work. All right, so now I want to show you how you might actually make a detector out of this. So here we're looking transversely through one of our detectors. What you might have is you might have a ring of these little tubes filling up that space to do it. So then if we have our charged particle going through, right, we could know it hit this one, hit that one, hit this one, hit that one, and we could use that information to build up a trajectory. And so that's what's known as a straw tube tracker. We have one of these in Atlas. It's called the Transition Radiation Tracker, or TRT. To do it. So that's one way that you can actually use these gaseous detectors. There's another way, and this is a pretty famous one because it won a Nobel Prize, which is the multi-wire proportional chamber. To do it. And you can also have a drift chamber here. There's sort of various different variants of it. The way that things are organized here, now you've got to imagine I'm drawing in 3D, so this is meant to be a plane. You have two different planes here. Actually, I want it to be longer, like that, okay? And then between the planes, you have wires. Okay, so imagine two flat planes, wires going sandwiched between them to do it. And these wires are going to be anode wires. And then these are going to be, both of them, are going to be cathode planes. And so here what you can see, right, is if you imagine your particle, again, passing through, you can collect up the ionization that you produce, these electrons, you can connect it up on all these different wires to do it. This one you'd orient a bit differently, right? Because it can actually measure, which of the different wires it would actually hit to do it. So, one tube there gives you just one measurement, maybe got timing, gives you something extra. This one you could know, which of your different wires would actually show. And so this is a different way of using the same principle, but a different geometry that you can actually put together. Well, so here, right, you could stack them around your detector, for example, to do it. And so they can be quite big. These end up often being muon chambers for us these days. And so they're, the this sort of size, those ones, those can also be muon chambers. You can also make big ones to do it. And so these are just showing you various different geometries, and this is not all, right? You know, there are many other ways of thinking about it, but different ways that you could think about doing it. One example, which you can look up if you're interested, is the time projection chamber. And this is actually the tracking detector that is used by Lhc. All right, yeah.
Is this same technology used in neutrino detectors?
I mean, these are just general techniques for detectors. So depending on what type of neutrino detector you want, it can be. This will only detect charged particles. So if you have a neutrino passing through, it's not going to be very useful. But often the neutrino detectors, right, you want a weak interaction with the neutrino, produce something which you may subsequently detect. Okay. So that's type 1. Then the other type are silicon detectors. These are newer. They've kind of come sort of from the 80s, 90s, but now they are extremely common. They are very light and compact. And they have excellent resolution. What I mean by that is, for example, if you think about our pixel detectors, which are some of the detectors we put really at the center to do very precise measurements, you can get to something like a 10 micron resolution in measurement to do it. Essentially, the way that we do them is we will have a layer of a sensor, right, a silicon sensor, and we do many different tricks with doping the silicon, okay? So it's usually made of silicon. Someone was telling me they work on diamonds. Actually, diamonds is another way of doing it, but not the expensive ones. You need to do the lab diamonds. And this is, for example, an N-bulk silicon detector. And then you might have some P plus silicon and no, N plus silicon going on here. And then what you also have is you have these little pieces that are sticking into your sensor, which are typically made, they'll be alternating silicon oxide and aluminum. But it's the same idea, okay? We have our charged particles, one's going down, passing through. It's going to pass through our silicon, and you want it to be doped because you want it to ionize the silicon in the same way. And we're going to produce positive, negative charged particles. And we're going to set things up. We're going to add an appropriate field such that the negatively charged particles are going to move down, positively charged particles are going to move up. And just like before, we're going to connect up that ionization. So more technically, what we actually do here is we apply an inverse potential to a PN junction. And what that actually does, it means that in silicon, we really have a large region of depleted charge. To do it. What this really means is that because we're using a semiconductor, that's why we chose to use silicon, it kind of behaves like an insulator, such that there's no current flowing, until you have that particle passing through, which produces ionization, releases electron-hole pairs that can drift apart and are really collected on each side of the sensor to do it. We have no time left, so I'll tell you 2 different applications, and then we can talk about them more tomorrow. Again, you can think, once you have this idea, right, you can think how you want to use it. One way would be a silicon strip. So this would just be a piece, really narrow in one direction, long in another. And you want to stick a whole bunch of strips together. In fact, what you do is you sort of stick them together at some little angle from each other, because then you can actually, say if I see it in 2, I can know the position quite precisely. The second type are known as the pixel detectors, which will have tiny squares or rectangles where we can measure. Sort of state of the art here is you might be able to get down to, say, 25 microns by 100 microns to do it. That's not what we have now. That's kind of what we are building to do it. And you can imagine combining these again, you have more freedom in terms of direction, right? If you're measuring in a small square, you can kind of choose how you would like to orientate that in your detector to be able to get a precise measurement. Any questions? Yeah.
Just briefly, can you tell me where I might see a silicon detector versus these gaseous wire chambers?
So, in fact, all of the detectors have silicon detectors. So CMS has an all-silicon tracker. They have a pixel and then a strip. Atlas has a mixture between silicon and gas. So we have a pixel, a strip, and then this TRT. Lhc, they have a pixel, and then they have a trion projection chamber, a gaseous detector. And LHCb, they have a Velo, which is actually pretty cool. It's a very tiny strip detector, but it's designed to actually move in and out of the beam pipe, depending where the beam is. So they get incredibly close to the beam to do it. So silicon is everywhere. And if you kind of look at the upgrades that people are building, everybody's also building silicon detectors to do it. By no means are we not going to use gas. But I would say that the smaller detectors, the ones closer to the beam, those are typically moving towards silicon. And then the larger volume ones, which can be cheaper to build with gas, those tend to be gas. That's very loosely speaking. Sure. Yeah? The shape of the pixels. So in Atlas, we decided to do rectangular pixels and to orientate them that the small one was in the transverse direction. CMS did square, so we get better transverse resolution. CMS get better longitudinal, but transverse actually helps you with the vertex. That's what I meant, it's a choice. Like, you get a trade-off in one way or the other, but it does matter and you can see it. Any more? All right, thanks everybody. I guess it's time now for a photo. Yeah.
Really nice, fascinating. Are you going to be around later?
Probably around lunchtime. I have various meetings and things otherwise.
Okay. I have tons of questions. I'll either ask you after the next class.
Yeah. Do it. But yeah, I'm happy to.